Hello everyone, this is Alanwar. I'm presenting our paper Event Triggered Diffusion Kalman Filters, which is accepted in the International Conference on Cyber Physical Systems, ICCPS, on CPS Week 2020. First, I will motivate briefly for using event trigger estimation. Then I will go through our paper. As you know, the performance of the state estimation algorithms depend on a lot of communication and computation on resource-constrained sensor nodes. The target of the event trigger estimation is to save the resources while preserving the estimation accuracy. One typical solution for event trigger estimation is the usage of error covariance matrix, which is one of the merits of the centralized Kalman filter. It's a perfect measure of the expected accuracy of the estimated state, so it can be utilized for regulating the resource consumption. Let's take an example. Consider a Kalman filter which takes measurement as distance between the nodes and take the local time as measurement also, and it estimates the location of the moving nodes and the global time. Now in this figure we show the trace of the covariance matrix. The blue line is the trace of the covariance matrix and the red line is the threshold. Whenever the trace of the covariance matrix exceed the threshold, we turn on the duty the system and the computation and the communication. Whenever it's lower than the threshold, we turn off the system, and so on. Our focus in this paper is diffusion Kalman filter. How to do the event trigger estimation on the diffusion Kalman filter. Diffusion Kalman filter consists basically of three steps: measurement update, diffusion update, and time update. In the measurement update, every node shares measurement with its neighbors, and then in the diffusion update they don't share measurement anymore, but they share the estimates, and finally in the time update they evolve according to some model. The question which we are trying to answer in this paper: can we still event trigger based on the P matrix without sharing the local covariance matrices between the nodes? Sharing the local covariant matrices between the nodes, or what's called the covariance intersection, is a great overhead. So we would like to investigate event trigger the diffusion Kalman filter without sharing the local covariance matrices. Can we still event trigger based on the P matrix? The short answer is yes, and this is our proposed algorithm. It's simply putting a condition on the weighted trace of the P matrix. Whenever it exceeds some threshold, we execute the measurement update and the diffusion update. Else we do some propagation update where we just take the old X and the old B matrices, and the time update is executed in all cases. The P matrix in the diffusion Kalman filter is not the global covariance matrix because of two reasons. First, every node has access to limited number of measurements, so it doesn't have access to all the measurement. So its P matrix is not the global covariance matrix, error covariance matrix. Also, in the diffusion update, every node combines the estimate from the neighbors without combining the P matrices of the neighbors, which result in difficulty in calculating the covariance matrix. we show in the paper that the global covariance matrix is proportionally directly proportionally to the P matrix, and we call this P matrix diffusion error covariance matrix. Our main theoretical result in the paper is the first. In lemma 1, we show that the event trigger diffusion Kalman filter is an unbiased estimator, and then we show the relationship between the global error covariance matrix and the local diffusion error covariance P matrix, which is available at each node. Then we apply our algorithm to localization and time synchronization. The state is the position, the clock offset, and the clock bias. The position consists of 3D positions, X, Y, and Z. Our measurement types are 3 types. First of all, type 1 is noisy counter difference, where node I send timestamp the current time to node J, which timestamp receiving the message, and calculate the difference between the two times. This measurement is used in time synchronization. The second type is noisy ranging, which is based on 4 timestamps, T0, T1, T2, and T3, and we use the C, which is the speed of the light, to calculate a single-sided range which has low accuracy in calculating the distance. The third type is accurate ranging, and it's based on 3 measurements or 3 messages, and it's calculated based on 6 timestamps, T0 until T5, and it's again using the round trip time and the response time to calculate accurate ranging Rij. Our system model is the normal nonlinear system model with the following state update function. Our measurement update function is as shown here, where the O is the bias offset, clock offset, and P is the position and B is the bias. Sorry, the O is the offset and B is the bias. Our test bed is a custom made board, and it consists of Cortex M4 processor. It has BTB network switch, and it's powered over Ethernet to reduce the cables in the lab. Our target has radio, ultra-wideband radio, which is used in calculating the distance, and it has inertia measurement sensor as well. This is our system. It consists of ceiling nodes, as you can see, and it has also motion capture system for getting the accurate location of the quadcopter while it flies in the lab. This is a sample of the result. The first figure is the 3D localization error, and the second subfigure, which is the most important one, is the trace of the error covariance matrix, or the local P. So we put a threshold on the weighted matrix P, and as you can see, we turn when the trace exceeds the threshold, we turn on the measurement and the diffusion. So the third figure is the measurement flag and the diffusion flag, and the fourth figure is the flag for running the time update. So when it's 1, it means we are running the measurement update and the diffusion update. When it's 0, it means we are not running it anymore. So as you can see here, we run the measurement and diffusion, then we turn off the communication and the computation. Then the uncertainty or the trace increase until it exceeds the threshold. Again we turn on, and so on. And as you can see, there is a drop whenever in the error whenever we turn on the measurement as expected. This is a main result. We calculated the percentage of message saving with respect to every value of the threshold, and also as a 3D localization error for fully connected network and partially connected network, and all the details are on the paper. Now I will show the test bed and show how to use our sample and illustrate the video, which is the output of our code. This is a quadcopter flying. And this is a custom ultra wideband board sending measurement on the ceiling. And this is a quadcopter. Now the blue is the true position of the quadcopter. The rectangles is the true position of the static nodes. The ellipses are based on the trace of the B matrices, and as you can, and the pluses are the estimates. And as you can see, the estimates is fixed and the uncertainty is increased, and then we turn on the system, the estimate jumps to the true position, and so on. So now, as you can see, it's turned off, and then we trigger the system to take measurement, and it will jump as you saw. Our data and code are fully available on this link, and it can be used in other estimations. You are welcome to use it. So in conclusion, we duty cycle the diffusion Kalman filter based on the local signal indicative of the estimation error. We show that we can still duty cycle the diffusion Kalman filter based on the P matrix, and we show the relation between the P matrix and the global error covariance. Thank you for your attention and for listening.